This is going to be based on joint works with Huang Yan, Spencer Brock, Masudivan Srinivasan, Xin Tong Yao, and Xingwen Zhu. And so this is an outline. First, I'm going to briefly talk about the classical theory of different integrals and the differential equation that they satisfy, called hypergeometric equations. Then I'll talk about the higher dimensional generalizations, which can be called period integrals, and formulate the same question of trying to find differential equations for these period integrals, which can be stated as a Riemann-Hilbert problem. Then I will introduce a so-called tautological system of partial differential equations, which are proposed as a solution to this Riemann-Hilbert problem in many interesting cases. Then I will describe some of its properties, emphasizing an approach from D-module theory. Then I will talk about some applications. So the theme is an interplay between special functions and complex geometry. So very roughly, a special function is something we are familiar with. Basically, it's some sort of multi-valued analytic function that satisfies a system of partial differential equations with polynomial coefficients. So we know lots of examples. But if you want some coherent theory, most likely we want some further restrictions on what class of function we want to consider. So what we're going to consider will be called hypergeometric functions. So there's a so-called Euler-Gauss hypergeometric function, which is defined to be a solution to this particular second-order linear differential equation, where this A, B, C are fixed complex parameters, and the equation is defined on P1. So every second-order linear ODE on P1 with three regular singularities can be transformed to this equation by a Mobius transformation. And so here, one see an explicit power series solution to this equation around z equals 0, provided that c is not a non-positive integer. And this is called the Euler-Gauss hypergeometric function. So now let me come to complex geometry and how that gets related with that. So let's recall the Legendre family of elliptic curves is given explicitly by y squared equals x times x minus 1 times x minus lambda, and is parameterized by this lambda, which is a complex number different from 0 and 1. So if you fix any lambda 0 in the base, then in a local contractible analytic neighborhood, we can identify the fiber topologically as a two torus. And so the first cohomology is identified with that of the two torus, which is c squared. Now, for example, we can look at this one form, dx over y, which we denote by omega. So that's a holomorphic one form on the curve. It's closed, so it defines a cohomology class, which varies holomorphically with lambda.
What's t? Did you say what t? Can you go back? What did you say? What
yeah, just
y lambda for each.
So it's just a two
okay.
Real two torus.
Okay. Yeah. Can you slow down just a little bit? In general, because these disappear, right? So we don't even get a chance to read these. Just slow down just a little.
Oh, sorry. Yeah.
Yeah.
Okay. So now, so what are the period integrals? And suppose we fix the basis gamma 1, gamma 2 of the first homology of the two torus. Then our cohomology class omega can be expanded in terms of linear combination of the dual bases, where these coefficient functions are period integrals. So they are integrals of our form over the chosen cycles. So a priori, these integrals are defined only locally. However, given any path in the base, you can do analytic continuation of them to get a possibly multivariate function. So in general, they generate a local system on the base.
So can you go back? The reason why these are only defined locally is because, can you go back?
Yeah, sure.
Is what because, no, forwards. Yeah, so because the basis gamma 1 and gamma 2 changes as we go around, this is why you're saying they're only defined.
Yeah, exactly.
Okay, but you've identified, so T is you've just identified a model at a fixed fiber here.
Yeah.
Topological model.
Yeah, in the local contractible analytic neighborhood.
Okay. Yeah.
So one can show that these elliptic integrals actually satisfy the Gauss equation. The proof is very easy.
Go back. There was an equation to that. Oh, that one. Yeah.
Yeah. Yes. To prove it satisfies this equation, we can just, for example, apply the second order differential operator to our one form and calculate. And the result is this. So it's a one form which is exact on the on y lambda minus a finite set of points. So we can certainly choose our representative one cycle such that they avoid this finite number of points. So by the Stokes theorem, we can show that this integral satisfies the differential equation, the Euler-Gauss differential equation. So now we know our integral of interest can be expanded as a linear combination of two basis solutions to this ODE. So the task of calculating the integral is reduced to calculate just two coefficients. And in order to get these coefficients, for example, we can look at how the family degenerates at num equals 0 a little bit more carefully. So the curve y sub 0 degenerates to a Lodel curve at num equals 0, and also our form divided by a pole. And if gamma 1 is a basic one cycle that avoids the node, then one should expect that this period integral is holomorphic around num equals 0, and in fact it is exactly equal to the Euler-Gauss hypergeometric function.
So what is a basic one cycle? Is the basic one cycle. So if there are two, why not is the nodal curve? Which one? Why not is a torus, right?
Why not is another curve?
Oh, it's the nodal one.
Yeah.
Okay, so there is a distinguished generator for the one cycle. Okay. That avoids the nodal.
Yeah.
So which one
is the vanishing cycle?
It's the one that's contractible.
Yes, yeah. It's the one that's a vanishing cycle.
Okay.
So if gamma 2 is another one, which is the basic one cycle that runs through the node, then we should expect that this integral will blow up along at lambda equals 0, and that's what is indeed happening. And you can calculate that is equal to this same Euler-Gauss function times log of lambda plus a unique power series, which is determined by the equation itself. So in summary, we can solve such an integral problem by relating the integral to the equation of the curves through these differential operators. So there's a similar story for hyper-elliptic integrals, and this interplay between such special integrals and geometry will be a spirit in which we're going to proceed to discuss their higher dimensional analogs. So are there any questions at this point?
Is there any way to make the text not disappear right after
Yeah,
you
that's
say it?
exactly right.
Not disappear what?
Is there any way to make the text stay up on each slide instead of disappear each time? Probably not.
Oh, probably not.
Not with that.
Sorry.
Yeah.
Yeah, maybe next time.
Yeah.
So some remarks. That there are more theory of special this kind of hypergeometric functions developed historically, often related with physics, and also the Garfunkel school initiated a systematic study of such hypergeometric functions of more than one variables. On the other hand, consideration of such pure integrals have also led to the development of course theory. So now let's talk about this higher dimensional pure integrals. So let B be a parameter space, which is a connected complex manifold, and E over B is a vector bundle, which we will assume to be equipped with a flat connection. And we denote the usual pairing between local sections of E and its dual by this bracket.
So those are the holomorphic ones. Or are we doing C infinity?
Holomorphic ones. Yes.
Okay. Yeah.
So suppose we fix a global section we call S star or of E star, which is non-zero. Suppose it exists. Then we define the period sheaf to be a sheaf generated by the local pairing between S star and locally constant sections of E.
Sorry, what was the pairing?
Can you leave it there for a second?
Yeah, so the pairing is between S star and the gamma, where gamma is a locally constant section of the dual bundle.
So S star is a section of what?
S star is a section of E star. So for example, in our previous example of the Lejeune family, S star is the one from omega sub lambda, and this gamma represented by 1 cycles.
Okay, so S is a section
S star is a section of E star.
star. Yeah. Okay. Oh, that's the pairing. We of course do the pairing between E and E star. Okay.
Yeah.
S is section star, and then going down again. Okay.
But gamma is a flat section, right?
Gamma is a locally flat section.
Yeah.
So let me be more specific. So for example, we consider Y to be a family of complex manifolds. Then we know that the Dirac comerge groups of the fibers is a vector bundle which is equipped with a flat collection called the Gauss-Manning collection. And now if we fix a section S star of E star, then locally, so recall that E star has fiber the Dirac comerge groups. So locally we can represent S star by a closed form on Y sub P. And we can represent a locally a flat section gamma of E by a cycle on Y sub P. So a local section of the period sheaf is represented by such an integral of the form S star over gamma. And this we call a pure integral of the family with respect to our choice of S star.
So is S star also flat?
No.
No, S star related.
Yeah.
Just not the constant that we have there.
Yeah. So now let me be a little bit more specific. Suppose I fix a compact Kähler manifold X, and I look at the family of smooth Calabi-Yau hypersurface given by sections of the anti-conical bundle. I also assume X is bundle. Then I will consider the vector bundle E star just as before. Then because Y sub B is now Calabi-Yau, so the line of Calabi-Yau form will form a subline bundle of each star, which I denote by H top here. And so a fact due to Nian and Yao says that this subline bundle admits a canonical trivialization. Here I denote by omega. So a remark is that although we restrict to the case of Calabi-Yau, but almost all results here generalize to general type. So now let's formulate our Riemann-Hilbert problem for pure integrals. It is the problem to construct a complete system of partial differential equations for the pure integrals. So this means two things. First, we hope to construct explicitly a system of differential equations for which pure integrals are the solutions. And second, we hope to prove any local analytic solution to the equation are these pure integrals. Or to be a little bit more flexible, if there are actual solutions, we need to understand precisely what those actual solutions are. And so the eventual goal is to study explicit solutions and also the monogamy of this local system. So there are several reasons we care about such things. So from physics, it's known that these pure integrals can be used to calculate so-called Yukawa coupling in type 2B string theory. And then by mirror symmetry, it can be used to calculate genus 0 Gromov-Witten invariants. And so from quartz theory point of view, we have local toric theorem for Calabi-Yau manifolds. So if we can calculate these pure integrals, hopefully it can help us understand the geometry better. And also, we are interested in studying the monogamy representation and cohomology. So in particular, for example, physicists are interested in something called large complex direct limit points, which is characterized as points where you have maximal unipotent monogamy. I'm going to come to some applications to these problems later. And then from D-module point of view, we explicitly realize the Gauss-Manin D-module in some interesting cases. And there are also some byproducts. For example, there are applications to the classical theory of GKZ systems, which I'm going to touch on later if I have time. So, what is known? If we have a hypersurface family in the projective space, then one has the Dog-Griffiths reduction of pole method, which is essentially an application of integration by paths. And this thing can be used to derive differential equations for these pure integrals. But there are some drawbacks. For example, it's in general complicated to carry out. So often works for one parameter family only. And also this method depends on some local choices. So for the Legendre family, such a method will yield precisely the Euler-Gauss equation that we have seen. And once this equation is found, because it's regular singular, you can use a Frobenius method to solve it. So more generally, if we have a hypersurface family in a toric ambient manifold, which roughly speaking is a manifold that contains an open dense torus, whose action on itself extends to the whole manifold. Then in this situation, suppose X is such a toric manifold with respect to a torus T, and we look at the generic Calabi-Yau hypersurface in X. Look at this family. Now I'm going to describe a system of equations for this for pure integrals of this family, and for this purpose, let's introduce a little bit notations. So let's denote the Lie algebra of the torus cross with C star by T hat. So because we have a torus action on the section space, and the C star acts by rescaling, so the D algebra T hat also acts on the section space, for which we can represent by a first order differential operator G sub y. And let beta be a character of T hat which takes 0 on T and takes 1 on the Euler operator as a generator of the rescaling action. Now, we know that each global section of the antichorical line bundle restricted to the torus can be represented as the Laurent polynomial in coordinates on the torus. And we record these exponents by mu sub I. So this mu sub I is going to be important data that will enter the differential equation. So it is well known that the pure integrals of such a family in a toric ambient satisfies a particular PE system called the GKZ hypergeometric system. This Gelfand, Kaparov, and Zanavinsky. And this system is defined by two groups of operators. The first group is called the box operator. And this box operator is defined explicitly as this. So whenever you have an integral relation between the exponents mu I, then you have such a box operator. And then the second group is Z sub y. Recall that Z sub y comes from the torus action, twisted by our choice of beta.
What's AI here? AI is the coordinates of the torus.
Yeah.
Okay. Why then? Why is it the coordinate? Or why is it the vertical coordinate?
Why parameterize the torus, the D algebra elements?
Oh, okay.
And you have a trivialization for k for minus kx. I mean, you're right. You said you can write these as. Can you go back?
Yeah, sure.
You can write these as Laurent polynomials, so sections. So are you using I mean, it should be Laurent polynomials times some form or something. Or how do you write these? How do you write sections of this as Laurent polynomials? Give some trivialization of kx. Oh, kx is trivial. No. How do you do that?
So, for example, if x is P2, and we have a polytope for x, and then we choose just for example, look at P2 and O of 3, which is an antichorical line bundle, and we represent each global section of this antichorical line bundle as itself divides by x0, x1, x2, where x0, x1, x2 are homogeneous coordinates of P2.
Okay, but there's no choice involved. I mean, on P2, it's clear.
And in each word you have a canonical choice for the anti-canonical divisor, and that's what he's taking.
So basically,
A meromorphic section of it. It gives you
Yeah, you just take the union of all the torus prime divisors, and this is your choice of it.
So basically, this comes from an ideal of the embedding of P2 into a bigger projective space given by the line bundle. So a theorem of GKZ says that the solution space of such a system is finite dimensional. But on the other hand, this system is never complete, meaning there are always more solutions than just the periods. And there are two conjectural ways to pick out the period integrals among solutions. It turns out that both conjectural ways are closely related to the thing that I'm going to talk about. And now these conjectural methods are better understood. So beyond toric, not much is known for this problem, except for some isolated examples. And so the problem was open, for example, for the case of hypersurface in a flat variety. Now I'm going to discuss a partial solution to this problem for a large class of manifolds, which includes the flat variety, the toric manifold, etc. So it's called tautological systems. So again, I need to fix some notations. So X is now a projective variety, and G a complex algebraic group this is E algebra G, and G X on X. L is a G equivariant base point 49 bounded on X. And let's denote the dual of the section space by V. So L gives rise to a morphism we call phi from X to a projective space PV. And let me denote the ideal by I sub V. And denote the natural pairing on V cross V star by the bracket. And we have the ring of polynomial differential operators on the section space, which I denote by dV star. So here is an example that we can keep in mind. So again, P2, and take G to be the orthogonal group PSL3, and L the anti-coordinate bundle O of 3. So V star in this case, as a representation of SL3, is the third symmetric product of the fundamental vector representation.
V was what, sections of L? Equivariant sections of, yeah, what was V? Go back, what was V?
V is the dual
Okay,
of the
dual
global
of
section
sections,
space.
okay.
Yeah. So phi now is this explicit embedding, and I sub phi is the quadratic ideal general.
Was it, you called it beta? Which is
Oh.
1 here, but what's the role of that in general, the beta?
Yeah, that's a very good question. So some particular value of beta corresponds to equations that come from such Calabi-Yau geometry. But you can also consider general beta.
So are there values besides 1 that lead to Calabi-Yau type geometries? Are there roots of unity here? What sort of betas show up?
So for this particular geometric setup, the relevant beta is beta equals 1.
You see systems where you have other special values of beta that are...
Yeah, for example, if you consider complete intersecting families, you will have a generalization of tau which involve more than one beta.
Mm-hmm.
And if you consider other piece of the period mapping, you will have some other values of beta. But you can also consider this problem in general for general beta, which doesn't necessarily come from geometry. So,
Sorry, I'm a bit confused about this theorem. Can you?
Yeah.
So, what role does G play? What if I just take G to be the trivial group? Am I allowed to do this?
You needed a finite number of orbits, you said.
Oh,
So
okay.
it's
Sorry, I
kind of looking
understand.
like a toric
Yeah.
variety but for other G.
yeah. But for example, if X is Pn, you can take either G to be the torus
Trivial.
or to be the full orthogonal group.
G is trivial. Oh, then you X would have to be minus the points.
And then the system I get is the same, or
Oh, they will be different.
it will be different? But
But the pure integrals
But pure integrals.
satisfy
Okay.
the equations. So, in order to understand this system better, we look at a solution rank. So this theorem is proved by Bloch, myself, and Lian, Srinivas, and Yao. Suppose G is semi-simple, and X is a projective G mod P, such that this technical condition holds. Then the solution rank of tau at any section is given by this formula, which is the dimension of middle dimensional cohomology.
What's Y sigma?
So Y sigma is the hypersurface.
Oh, X is the ambient space, Y sigma is the particular hypersurface.
Yes. And the solution rank is given by the dimension of middle dimensional cohomology of this alpha and right, the complement of Y in X. So, two remarks. It was conjectured that this technical assumption can be removed. This one. And which seems to be difficult to check in general.
What's the technical assumption?
That's
That's rejection.
the suggestion. Right.
Okay.
And the proof, the rough idea of the proof is to use a method of Dimka to interpret this algebraic Dirac cohomology by a Lie algebra homology of a certain infinite dimensional G module.
Wait, so the dimension of that middle cohomology there,
Yeah.
Can't we write that in terms of the cohomology of y sigma by the
Yeah, there's a short exact sequence.
yeah, the short exact sequence, well, and then also the Lefschetz hyperplane theorem, right? I mean, so
The y sigma can be singular.
Oh,
Yeah, yeah,
y
y
sigmas
sigma.
can be singular. So in the case where sigma is smooth,
It's all the same, right?
Yeah, when in the case y sub sigma is smooth, this thing can be calculated by the hypersurface cohomology plus the primitive cohomology of the ambient.
I
But-
see, it's the primitive cohomology plus the.
But when y is singular, it's complicated. And so later we proved a theorem with Nian and Zhu, which basically removes this technical condition entirely, and the same conclusion holds. So here is an immediate application of this result. Recall the pure integral of a family are solutions to tau. So now the question is when tau is complete, meaning any solution is a period. And the corollary is that in the case X is projective homogeneous space, then tau is complete if and only if its middle dimensional primitive cohomology vanishes. And in the case where this primitive cohomology doesn't vanish, the actual solutions are precisely integral over the same top form over these primitive cycles.
Can you remind us what the primitive cohomology is? What's it mean again?
So you have a SL2 action
Yeah.
on the total cohomology of X. Primitive cohomology based roughly consists of highest weight vectors.
So we're looking in the middle cohomology. We're picking off the one that just comes from the trivial representation of SL2? Is that what you want for the primitive? I mean, we have ones that come from that might live in the middle, but are coming from. That are not highest weight. So you just want the trivial.
Yeah.
Got it. Okay. And if that's zero, what are we saying? Then the tau is complete. Okay. Then all the solutions come from these geometric solutions.
Yeah, then all solutions actually come from periods over the hypersurface. And if it's non-zero, then the actual solutions come from an integral of a meromorphic top form.
I see. So most of the things we know, like, well, RK, most of the things I know. I mean, the homogeneous spaces for like a Lie group, this is going to be true, right? Or not
I
necessarily?
think it's very rare that this is true for.
Really? Like for projective space, maybe I misunderstood. This is true for
Yeah,
projective.
it's true for projective space.
Oh.
Exactly. That's what I'm going to talk about next. Yeah.
But for Grassmannians, it's not true?
No.
Oh, because you can have a bunch of them. Wait.
Yeah. So for
Right.
for projective space, this is true, and therefore tau is complete. And this was conjectured by by physicists and also Hossong Nian Yao in 1995. So the basic idea to prove such a geometric rank formula is to use the theory of D modules. Basically, we can understand this tau as a D module very nicely, and therefore we can apply the Riemann-Hilbert correspondence in its derived category version due to Kashoar and Manholt, and then prove the rank formula. So now I'm also going to talk about an algebraic rank formula. So let's fix a very ample line bundle L over a projective G variety X, and let me denote the coordinate ring of X with respect to this topological map by R. And again, V is the view of the section space. And let G star denote the view representation of G hat, which is G direct sum C on V. And then let F be the universal section of L. There are two observations. First, this strangely written vector space R over V times e to the F. So recall R is the homogeneous coordinate ring, and V is the dual of the section space. So this first a priori is a vector space, and it has a natural dV star module structure given by something like a half Fourier transform.
What is it, sir? What is e to the f?
Well, I write this as R of V times e to the f in order that I can write this D module action in a simple way. So this as a vector space, of course, is isomorphic to R of V.
Yeah.
But if I write in that way, then the D module action I have to write by a complicated formula.
What is f again?
F is a universal section. Is the universal section of L.
Oh, so, okay, we rewrite every homogeneous coordinate by multiplying by, but you're taking e to the f. Oh, okay, that which has graded piece. I guess I don't know what you're doing.
So maybe I'll tell an example in a moment.
Okay.
So the second observation is that the operators coming from the dual representation of G hat actually commute with this D module structure. So the image of the star action is a sub D module. And a theorem is that there is a choroidal D module isomorphism between tau and this quotient D module. So as a corollary, if X is a projective G space, actually in this corollary homogeneous can be deleted. Then the solution, the space of solutions of tau at any point B is choroidally isomorphic to the dual of the Lie algebra coinvariant space of the Lie algebra G hat acting on this infinite dimensional vector space. So so let me describe this action in a little bit more detail. For the example of X is P n minus 1 and G is P XL n, and L is the antichorical line bundle O of n, and Xi are the homogeneous coordinates of X. Then in this case, R is the ring generated by total degree n monomials of this Xi. And so what this Lie algebra actually is that it's represented by differential operators of the form Xi times partial over partial Xj. So it's just a G. I'm going to line bundle algebraic rank formula. So we're interested in looking for points where either side is one-dimensional. For simplicity, we can call such points a rank 1 fiber. N explicit point. So here X with these subscripts are the political coordinates. So this is just a particular section. For example, if you take K to be 1, you recover the familiar hyperplane configuration for P n minus 1. And for K equals 2, it is X 1, 2, X 2, 3 multiplied all the way up to X n1.
Are the singularities at these points always normal crossing divisors?
Might not.
We don't know, or maybe not.
I'm not sure, but probably not for Grassmannians. So for these points, we can show that they are rank 1 by either the algebraic rank formula or the geometric rank formula. But to show their rank 1 is not very trivial. So next, we have two generalizations of this result. First, we can glue together lower dimensional rank 1 fibers in smaller Grassmannians to generate rank 1 fibers in an arbitrary partial flat variety of type A. And second, we can construct directly a rank 1 fiber there is a natural stratification of the flat variety.
Crossing advisors to those words.
I,
The boundary of the stratification is normal crossing.
uh,
The
I think that there are some results on
So
the
the
singularities.
stratification is with Richardson varieties.
Yeah, you take all the union of all the codimension one Richardson varieties. Is that a normal crossing that's divided by smooth?
So as far as I know, probably there are a lot of crossing in general, but they have some nice characterizations. So the work of David Spear and Thomas Nam and Anand Grusen who work on such things. So for the Grassmannian, this construction recovers the point I just talked about. So for the toric case, we can apply our algebra rank formula to give a one-line proof of a previous result on such points. So I'm going to skip this probably, and also so skip this. So let's talk about application to classical theory of GKZ system. So actually, a much more general formula is proved, which gives the rank as a compact support middle cohomology of a certain perverse sheaf. And this rank formula applies for an arbitrary G manifold with a finite number of G orbits. So before this, the rank was only known for GKZ at a generic point, and now we have a formula at arbitrary point. So let's see what the formula says for toric variety. For example, you take a projective space again, then tau reduced to a GKZ system. And so we know, as we said, the pure integrals of the hypersurface are solutions to this GKZ system, but it also has some other solutions. So what is the nature of these other solutions were not very well understood. But now we can describe them very explicitly as integral of a monomorphic top form with a log probe along the hypersurface over cycles and specific chains in the open complement. So what are those chains? These chains are chronologically constructed by a spectral sequence converging to a genetic store of the solution sheaf of the GKZ system. So by a compact support middle cohomology or perverse sheaf. So the chains can actually be described very explicitly for were series and system. So just some concluding remarks. Most of the results here carry over to general type complete intersection, and also to the full period mapping with some extensions of the method.
So instead of just anti-canonical sections, you're doing what sections? Complete intersections, but Claudiel complete intersections, or
Also general type.
general type.
Yeah. Yeah. Then we need some extensions of the definition of the system. So it provides a new approach to study a generalization of hyper-even integrals. Tautological system reduced to GKZ, and if X is toric, instead we take the full orthogonal group. That's a so-called extended GKZ system. And in this case, tau reduces to that extended GKZ system. And if X is spherical variety, it reduces to a Karpov system. So it unifies and generalizes all these above class of special functions, and because of geometric representation theory, we have a good control of it. So thank you for your attention. How? So we can choose G. If you consider the spectral variety, certainly it's applies to this situation for B. Also,
Oh, I see. And also G, you could pick G as well.
yeah.
Oh, I see. So.
Yeah, I was caught. I ended up talking to many students for a while.
Okay.
And he had a lot to say, so
Okay.
I ended up being late. But I did find it out.
Oh, good, good.
Yeah, I wanted to talk to him
And
because.
you two met already now?
Yeah.
Good, good.
Let's look.
Nice to meet you. Yeah.
I'm sure.
So,
Wherever it's good.
Who's coming to bags? Anybody coming to bags?
I wish I could, I cannot come to bags.
Well, I know it looks really good.